Ever notice how ads always pop up at the worst moments? When the killer's identity is about to be revealed. During that perfect meditation flow. On Amazon Music, we believe in keeping you in the moment. That's why we've got millions of ad-free podcast episodes, so you can stay completely immersed in every story, every reveal, every breath. Download the Amazon Music app and start listening to your favorite podcasts ad-free, included with Prime.
You might have heard about this almost imperceptible whoop sound.
Ah, yes. The sound interpretation.
Yeah, that's supposedly the sound of two black holes colliding, like over 1 billion light years away.
It's credible, isn't it?
And even more incredible is how that faint cosmic murmur unlocked a completely new way for us to understand the universe. You sent in a fantastic stack of articles on this, and today, well, we're diving deep into the discovery of gravitational waves. We're aiming for that next big aha moment for you.
Exactly. And we've pulled together a really rich set of sources for you. We've got the BBC's report on the Nobel Prize, tons of detail from the LIGO lab websites, both Caltech and MIT.
Right.
There's also an insightful Q&A with Kip Thorne from the National Science Foundation. The original detection announcements from MIT and Caltech.
The exciting stuff.
Oh, yeah.
Yeah.
Plus the big scientific paper from the LIGO Scientific Collaboration and some great explainers from space.com and nobelprize.org.
So our mission today is to unpack these ripples in spacetime.
That's the plan. We'll explore what they actually are, the decades it took to even find them, and why this discovery, which won a Nobel Prize, has just fundamentally changed how we see the cosmos.
And we'll keep it engaging, try to steer clear of the super heavy jargon.
Absolutely.
Okay, let's get into it. The whole story really starts with Albert Einstein, doesn't it?
Yeah.
Back in 1915, his general theory of relativity.
That's the bedrock. And baked right into that theory was the prediction of these things. Gravitational waves.
The analogy space.com used is pretty helpful, thinking of massive things like stars or black holes as bowling balls on a stretched rubber sheet. They warp space-time.
Right. But Einstein's theory went further. It predicted that if these massive objects accelerate, say, orbit each other or collide, they don't just warp space-time statically, they actually cause it to, well, ripple outwards.
Like waves spreading out.
Exactly. Gravitational waves traveling at the speed of light. And the more massive the objects and the more violent the event, the stronger the waves.
But here's the kicker. Einstein himself, even though he predicted them, he was pretty skeptical we could ever actually detect them.
He really was. He thought the effect would just be far too tiny, way too faint for any conceivable technology to pick up.
And the BBC and MIT News mentioned he wasn't alone in thinking that. So if Einstein was doubtful, what were the massive challenges? Why was it so hard?
That's a key question. It really came down to needing decades, literally decades, of technological breakthroughs. The LIGO lab facts point out that when the NSF first funded LIGO back in the early 90s, a lot of the tech just, well, it didn't exist.
Wow.
It was a massive gamble. High risk, high reward, as the NSF put it. They were pushing the absolute limits of engineering.
High risk is right. So it took something like 3 decades of constant innovation.
Pretty much. Engineers, scientists just relentlessly pushing forward. And the result of all that effort, LIGO, the Laser Interferometer Gravitational Wave Observatory.
These enormous L-shaped detectors, one in Hanford, Washington, the other down in Livingston, Louisiana.
Yep, 3,000 kilometers apart, operating perfectly in sync. That separation is crucial.
And the scale. It's just hard to wrap your head around. Each arm of the L is 4 kilometers long.
4 kilometers.
Yeah.
And inside those arms, an incredible vacuum. We're talking 1/billionth of an atmosphere. It took over a month just to pump the air out. They're apparently the 3rd largest vacuum chambers in the world.
And the pressure on those tubes. The LIGO facts mentions something like 155 million kilograms of air pressure pushing down on each arm, held back by just millimeters of steel.
It's astounding engineering.
Right.
Like thousands of elephants sitting on them.
And they even had to account for the Earth's curve, right? To make sure the lasers hit the mirrors properly.
They did. Otherwise, the laser beam would shoot off about a meter above the target mirror at the other end. Just think about that precision over 4 kilometers.
Okay, so you have these massive, incredibly precise instruments. How do they actually detect a wave that's supposedly weaker than anything Einstein thought possible?
It boils down to something called laser interferometry. Basically, you take a laser beam, split it in 2, and send each half down one of the 4-kilometer arms.
Okay.
The beams bounce off mirrors at the far ends and come back to meet where they started. Now, if a gravitational wave passes through, it momentarily stretches space-time along one direction and squeezes it in the perpendicular direction. So one arm gets slightly longer, the other gets slightly shorter, just for an instant.
An incredibly tiny amount, I imagine.
Infinitesimally small.
Yeah.
This changes the travel time for the laser beams just enough so that when they recombine, their light waves are slightly out of sync.
And that out-of-sync pattern is the signal.
That's the fingerprint. The interference pattern shifts subtly, and that shift tells us a gravitational wave just passed through.
And the sensitivity needed is, well, the LIGO facts say, it's like measuring a change smaller than 1/10,000th the width of a proton.
It's almost unbelievable sensitivity, like measuring the distance to the nearest star, Proxima Centauri, accurately to within the width of a human hair.
Mind-boggling. So after all that work, all those decades, the moment finally came.
It did. September 14th, 2015, 5:51 a.m. Eastern Daylight Time. Both LIGO detectors, Hanford and Livingston, registered a signal, almost simultaneously.
Wow.
That was it. Confirmation of one of Einstein's major predictions, and as the news report said, it opened a totally new window on the universe.
And the source. What created that first detected wave, GW 150912?
Something truly cosmic, the merger of two black holes. One was about 29 times the mass of our sun, the other around 36 solar masses.
And they were far away.
Incredibly far, about 1.3 billion light years away, somewhere in the southern hemisphere sky.
The energy release must have been immense.
Astonishing. In just that final fraction of a second before they merged, the LIGO scientists calculated that energy equivalent to about 3 times the mass of our sun was converted purely into gravitational waves.
3 suns worth of mass, just gone into waves.
Yep, directly into gravitational wave energy. EMCHX in action on a cosmic scale. The peak power output, just for that moment, was estimated to be 50 times greater than the light emitted by the entire visible universe combined.
That number is just staggering, 50 times the light of the whole universe.
It really puts into perspective the kind of events these waves can reveal. Events totally invisible to traditional telescopes.
And the slight time difference in arrival between the Louisiana and Washington detectors helped narrow down where it came from.
Exactly. Livingston got the signal just milliseconds before Hanford, which gave them a rough patch of sky to point to.
You mentioned a sound earlier, that chirp. Tell us a bit more about that.
Right, so obviously gravitational waves aren't sound waves. They don't travel through air or anything. But if you take the detected wave, signal, the frequency and amplitude changing over time and convert it into the human hearing range,
you get a sound.
You get this characteristic chirp. It starts low and quiet, then sweeps up in pitch and volume very quickly as the black holes spiral faster and faster, closer and closer, right before they merge. Whoop!
It makes it a bit more tangible, I guess.
It does. It helps visualize this incredibly violent cosmic dance.
So, okay, confirming Einstein is huge. But this detection, GW 150911, its significance goes way beyond just proving a theory, right?
Oh, absolutely. For centuries, we've studied the universe using light electromagnetic radiation. Visible light, radio waves, X-rays, gamma rays.
Right, our traditional telescopes.
Exactly. But this was the first direct observation of the gravitational waves themselves. We weren't just inferring their existence anymore.
Like Holson-Taylor did with the binary pulsar, they got a Nobel for indirect evidence showing the orbit shrinking.
Precisely. That was brilliant work, confirming the energy loss matched predictions. But LIGO felt the wave pass through Earth. It directly measured that distortion of space-time.
And these waves carry different information than light does.
Completely different. They give us unique insights into the events that create them, colliding black holes, neutron stars, and into the nature of gravity in extreme conditions. And crucially, as the NSF notes, they travel unimpeded across the cosmos, even from the very early universe, when it was opaque to light.
So they could potentially tell us about things light can never show us.
That's one of the most exciting prospects.
I remember seeing a quote from Olga Botner about this.
Yes, from the Royal Swedish Academy of Sciences, quoted by the BBC. She said, "The first ever observation of a gravitational wave was a milestone, a window on the universe, a perfect summary."
And it kicked off this whole new field, multi-messenger astronomy.
That's right. The idea is to combine the messages we get from gravitational waves with the messages from light and other particles like neutrinos.
Can you give an example of why seeing the same event with different eyes is so useful?
Sure. A great example was the detection of 2 neutron stars merging in 2017. LIGO and Virgo detected the gravitational waves. And almost immediately afterwards, telescopes across the globe saw a burst of light, a kilonova, coming from the same spot in the sky. Observing both the waves and the light confirmed theories about where heavy elements like gold and platinum were created. It gave us a much richer picture than either method could alone.
So you get the whole story, not just part of it.
Exactly. The NSF and Space.com really emphasize how powerful this synergy is.
And it wasn't just a one-off discovery, was it? LIGO kept detecting things.
Oh, definitely not. The floodgates opened. Many more black hole mergers have been detected since 2015. And that neutron-star merger was another huge milestone.
Kip Thorne mentioned in that NSF Q&A that detections are becoming almost routine now.
Yeah, with the upgrades to advanced LIGO, he said they're seeing smaller black hole collisions roughly every other day now. It's becoming a regular survey of the universe's most violent events.
It's not just LIGO anymore, right? There's other work happening.
Absolutely. A really exciting recent development came from the Nanograv collaboration. They didn't use interferometers like LIGO. Instead, they used pulsars.
Pulsars. The spinning neutron stars.
Exactly. They act like incredibly precise cosmic clocks. Nanograv monitored dozens of these pulsars over many years, looking for tiny, correlated changes in the arrival times of their radio pulses.
And those changes are caused by gravitational waves.
That's the idea. Really long wavelength gravitational waves, perhaps from supermassive black hole binaries across the universe, stretching and squeezing space between us and the pulsars, subtly altering the timing. They announced evidence for this low-frequency gravitational wave background.
So different methods detecting different kinds of waves.
Precisely. LIGO detects high-frequency waves from individual relatively quick events, like mergers happening in fractions of a second. Nanograv is sensitive to waves with periods of years, even decades. It's like hearing the whole cosmic orchestra from the high notes to the deep bass rumble.
Amazing. And naturally, this huge achievement was recognized. The Nobel Prize.
Yes, in 2017, the Nobel Prize in Physics went to Rainer Weiss, Kip Thorne, and Barry Barish.
The key figures behind LIGO.
Right. The citation was for decisive contributions to the LIGO detector and the observation of gravitational waves.
And they each had crucial roles. Weiss with the initial design concept.
Thorne providing a lot of the essential theoretical framework and predictions.
And Barish really leading the massive complex project to actually get it built and working.
Exactly. The BBC piece highlighted how their different strengths were essential. But, it's also important to remember, as people like Sir Martin Rees pointed out, that LIGO's success was built on the work of over 1,000 scientists and engineers.
A huge collaboration.
Truly.
Yeah.
Modern big science often is, which the Nobel rules sometimes struggle to fully capture.
So, looking ahead now, what's next for gravitational wave astronomy? It feels like we're just scratching the surface.
We really are. The future looks incredibly exciting. LIGO itself is constantly being upgraded for even greater sensitivity.
And the network is growing.
Yes, that's key. We now have Virgo in Italy and Kagra in Japan online, working in coordination with LIGO. And there's potential for a third LIGO detector in India.
Why is having more detectors so important?
It dramatically improves our ability to pinpoint where the waves are coming from in the sky. With just 2 detectors, you get a rough arc. With 3 or more, you can triangulate the source much more precisely.
Which helps for that multi-messenger follow-up with telescopes.
Exactly. And it also lets us measure the properties of the source, the masses, the spins, how the waves are polarized, with much better accuracy.
Testing Einstein's theory in new ways.
That's a big goal. Pushing general relativity into extreme regimes it's never been tested in before. And maybe, just maybe, finding places where it might break down.
And the ultimate prize, detecting waves from the Big Bang itself.
That's the dream for many in the field. Detecting primordial gravitational waves, relics from the universe's very first moments. That would be revolutionary, giving us a direct probe of physics at energies far beyond anything we can achieve on Earth. Future instruments, perhaps space-based ones, might get us there.
So wrapping this up for you, our listener, what's the big takeaway?
Well, it really means we've achieved this monumental leap in how we can study the universe. We've gone beyond just seeing the cosmos with light.
To actually hearing it, in a sense, through these ripples in spacetime itself.
Right. You now have, hopefully, a solid grasp of what gravitational waves are, the incredible journey it took to detect them, and why this whole field is such a powerful new tool for discovery.
And here's something to really think about. Those waves LIGO first detected, they literally warped spacetime here on Earth by less than the width of a proton. An unbelievably tiny disturbance. Yet, that tiny wobble carried information across 1.3 billion years, revealing an event more powerful than all the starlight in the visible universe combined. It makes you wonder what other profound secrets are hidden in these faint whispers from the depths of space. Absolutely. This deep dive well, it's really just opened the door. If you're intrigued, and we hope you are, definitely check out the LIGO laboratory websites or the Nobel Prize site for more background. Or look into multi-messenger astronomy specifically.
There's so much more to explore, a whole universe of knowledge, quite literally.